Hi, my name is Madeline Murchland, and I'm a senior geology major at Miami University, where I also work with Dr. Rakovan on research in mineralogy. Today I'll be talking to you guys about a project that I started working on over the summer, which is on fluorescent zoning and spectroscopy of apatite crystals. So the exact way the mineral fluoresces is controlled by a variety of different factors, from growth environment to light source. Apatite in particular has a really incredible variation in fluorescence. This is mostly because the structure of the mineral is so accommodating and can take in over half of the periodic table of elements and substitutions. This includes activators like manganese 2+ and 3+, as well as the trivalent rare earths and coactivators like lead, along with some other quenchers. All of the combination possibilities of these, along with crystal field shifts in the structure that can occur from substitutions, is what gives apatite the wide variety of fluorescence that you see. This piece in particular, from the Dera-Ipesh pegmatite field in Afghanistan, fluoresces really homogenously yellow in shortwave. As you'll see later on, that's not always the case with apatite, that it will fluoresce one color. For some minerals, the exact color and intensity of fluorescence is heavily dependent on the light source. For UV lights, you have long-wave, mid-wave, and short-wave sources. This piece from the Sauerberg mine is made up of fluorapatite and fluorite on quartz, where both the fluorapatite and fluorite fluoresce. In long wave, the fluorapatite is yellow and the fluorite is blue, while under the midwave source, the fluorapatite is pink-orange and the fluorite is more of a purple. And if you look at the 001 of this apatite, this one in the left-hand corner of the picture, it's also very apparent that the midwave source shows more concentric zoning. While the rings can be vaguely observed in long wave, the midwave source causes a more dramatic difference in the color between the zones. Zoning of fluorescence was one of the major interests of this study, mainly because it's the result of spatial differences in the activators, coactivators, and quenchers. And apatite can show multiple different types of zoning. Firstly, there's concentric zoning, which is shown really nicely in this piece from Penasquera. Concentric zoning is the product of changes in the growth environment, either in the physical or chemical properties. So magma compositions can mature as they cool, and that can be reflected in the physical appearance of the crystal, as its outer layers will have a different composition than the core. These zones also have a crystallographic implication as they follow the orientation of crystal faces. So that's what you're seeing in this diagram, where an apatite crystal has pinacoid, prism, and dipyramid forms. This slice through that shows concentric zoning core to rim, where the zones actually also show the boundaries between adjacent sectors, which are marked between the breaks in the zones there. So this is an example of a concentrically zoned apatite from Bolivia that shows very distinct, very coarse concentric zoning under a midwave source. This is one that we did spectroscopy on. So the way that we identified these peaks was comparing them to other studies that are in the literature. And with this one, it looks like the long-wave fluorescence spectra for the rim of the zoning is likely caused by europium 2+.
The zoning shows many more sharper peaks, which typically points to the trivalent rare earths as activators. That first peak around 480 nanometers has been identified as dysprosium 3+, the second peak around 570 as well. The other three peaks are likely from samarium 3+.
Another type of zoning that can be found in apatite is sectoral zoning. Sectoral zoning results from the difference in chemistry between domains of a crystal that are not related by symmetry. So I won't go into it too much, but think about crystals growing from a center nucleus and atoms attaching onto that and eventually growing out to form flat faces. So those faces that are related by symmetry are form. And forms can have different affinities for specific atoms or elements that differ from other forms on the same crystal. Depending on whether or not those atoms are activators of fluorescence is what will lead to sectoral zoning of fluorescence. So in the diagram here, you see the domain that extends underneath the 010, which is not related to the 001, which also has dotted lines to represent the domain that's under that. So think about there being a difference in affinity for atoms between these two faces. Therefore, they have different chemistries and potentially different zoning. This Huanzala fluorapatite is a great example of sectoral zoning because it's not common for apatites that show this type of zoning to be as nicely transparent. The transparency actually lets you see the sector boundaries at depth within the crystal, and those are highlighted here in that yellow dotted line. So you can see the difference in sector zoning between the blue-purple regions and the pink regions. Here's an example of a Yayawa apatite with fluorescent zoning between the pinacoid and the prism faces. The color is phase-specific here because the crystal is not transparent enough, like the last one, for the entire sectors to be observed. Here is the long-wave fluorescence spectra for the prism of that crystal. So you see that same europium 2+ peak that we saw back with the Bolivian apatite, along with samarium 3+ as well, but you'll notice that that peak is much broader, and those 3 distinct peaks that you get from the trivalent rare earths aren't as distinct here. As is common in apatite, it looks like the fluorescence is caused by a combination of elements, potentially samarium 2+ and manganese 2+. As for the purple that's observed on the pinacoid, this is most likely from the incorporation of europium 2+, represented by that 450 nanometer peak, and manganese 2+. Here's just another nice example of sectoral zoning from a different locality. This is a fluorapatite from the Ashio mine in Japan. The prism faces luminescent bright purple-white and shortwave, while the pinacoid faces luminescent pink. Another control on fluorescence is the type of occurrence that the apatite forms in, because this is really what controls what elements are available to incorporate into the crystal. A common environment for apatites is iron oxide apatite deposits, or IOAs. The example here is from the Calumet ore body in Iron Springs district of Utah. The formation of these deposits is kind of controversial because there's not really an agreed upon origin for the ore forming fluids, but magnetite and sometimes hematite are the minerals of economic interest here, while they're also known to produce apatites with an enrichment in REEs. Magmatic hydrothermal deposits are one of the most common occurrences of apatite. They refer to environments where the aqueous solutions that deposit the ore minerals are derived from the magma source. These deposits are really rich in metals, like is the case with Penasqueira, which is a tin tungsten deposit. The example here is from Broken Hill in Australia, which is a lead, zinc, silver ore deposit. And as we all know, apatite also commonly occurs in granitic pegmatites all over the world, this example being from Pakistan. So this first example is of a fluorapatite on magmatite from the Three Peaks in Utah, which is part of an iron oxide apatite deposit, and the example that you're seeing is luminescing under midwave, as is the case with most of the pictures in this PowerPoint, even though our data was collected in longwave. So this image is our spectra from the fluorescence emission of this particular apatite from Three Peaks. As you can see, we couldn't get a lot of data off of this crystal. The emission was really low when we tried to get a spectra of it, but given where that peak placement is, it could potentially be samarium 3+. Another example of an IOA apatite is this one from Bach in Iran. Here is the spectra for that last apatite that you saw. You can tell that the peaks that you see there don't really match to anything that we were finding in the literature. So what I did was put on lines for dysprosium 3+, europium 3+, and terbium 3+, right where their centroids would be. It looks like it's possible that the emission from this is a combination of the 3 of those. Moving on to magmatic hydrothermal deposit examples, here is a very nice sectorally zoned apatite from Yayawa in Bolivia. Here is the spectra for those prism faces, again with the europium 2+ and samarium 3+ coactivation. As for the pinacoid faces that are luminescing that kind of blue-purple, you see a really high europium 2+ peak compared to a lower intensity samarium 3+ peak, which suggests that the difference in color between the prism and pinacoid is due to different amounts of these two elements. Our next example is from another mine in Bolivia, with this fluorapatite luminescing more of an orange to pink color. This is a very different, distinct spectra to what we've been seeing before, where you have europium 2+ and dysprosium 3+ peaks being very close together, and those 3 broader samarium 3+ peaks towards the upper half of the spectra. Note that because these peaks are a little broader, it's possible that there's, again, coactivation with manganese. Our next example, moving on to a pegmatite example, is fluorapatite from the Foot Mine in North Carolina. We were interested in this apatite because it luminesces a very distinct red color that you don't see very commonly. And the fluorescence that we were getting from it, as far as emission-wise, looked like it was potentially europium 3+, which is not what we were expecting. The next set of apatites that you're going to see are all going to be fluorescing in a very similar color under long wave, which is more of an orange yellow to a very bright yellow. And they're all going to be from the same kind of occurrence, which is a granitic pegmatite. This example of fluorapatite is from Maine, and the spectra that we got for it looks like this, with that dysprosium 3+ peak towards the lower half of the spectrum, with these very interesting looking samarium 3+ peaks in the upper half past 550 nanometers. Again, those samarium peaks are likely due to some kind of coactivation. This next example is from the Harvard mine in Greenwood, Maine. The spectra for this, despite having a very similar color of fluorescence, is quite different than the last one that we saw, with instead of those trivalent rare earth peaks, you see just a single manganese 2+ peak right past 550 nanometers.
Our next example of fluorapatite is this really brightly fluorescing one from Pakistan.
The spectra for this shows europium 2+ and dysprosium 3+ peaks with really low intensity, so the majority of the fluorescence is being caused by manganese 2+. You have that same large manganese peak at around 560 nanometers that you saw with the Harvard mine fluorapatite. Our next example of a yellow apatite is that same one that we saw at the very beginning of the presentation from Dera-e-Pesh pegmatite field in Afghanistan. In this spectra, you see a little bit of a higher dysprosium 3+ peak, but again, that large manganese 2+ peak at around 560, 565 nanometers. You also have smaller peaks that are coming off of that large peak for manganese, which suggests that samarium 3+ and manganese 2+ overlap here, and so you're only seeing those last two samarium 3+ peaks. Our final example of a yellow fluorescing pegmatitic apatite is from the Harding mine in New Mexico. These apatites are known for being manganese dominant, so it's interesting that our spectra showed that we still had a little bit of a peak for trivalent dysprosium, along with trivalent samarium, like we saw with the last one, but it is dominated by manganese 2+. This final graph shows all of the spectra for the previous yellow fluorescing apatites overlaid. So accounting for intensities, you can still tell that all of these apatites were dominated by manganese in terms of activation. Harding, New Mexico apatite is in green, the Dera-e-Pesh is in red, Harvard mine yellow, and then the Pakistan apatite in blue. While they're all dominated in manganese, all except for the Harvard mine apatite have some amount of rare earths, differing amounts compared to each other, that are likely controlling the exact shade of yellow fluorescence that you end up seeing. Here is my works cited, including all of the pieces of literature that I used to compare my spectra to. Lastly, I'll leave you with this very nicely concentrically zoned fluorapatite from Penasquira, and I'm happy to take any questions. Thank you for listening.